Okay, we're live. Hello, volunteers. I'm Megan. I'm your project coordinator from the Transcription Center, and I'm delighted to be working on a snowy day and not letting any of that hold us back. The snow must go on, and so must the DASCH Hangout. We are speaking with a group of people today. You can see many heads in the Hangout for our Google Hangout, and we'll have Josh Grindlay, who's the Robert Treat Paine Professor of Practical Astronomy from Harvard's Department of Astronomy. We have David Slisky, and we also have Lindsay Smith, who've been working with you on the DASCH project. And then I'll let you all say hello.
Hello, everybody. Josh here. And thank you in advance for all the work you're doing.
Hi, I'm Lindsay. Nice to meet you.
Hi, and I'm David, and we hung out earlier and talked a little bit about some of the details of the project.
Excellent. And we also have three of our volunteers in the Hangout today who have been through the experience of transcribing these logbooks both in the Transcription Center and out of the Transcription Center. And we hopefully will have some great discussion at the end of our talk today with some questions from them. Volunteers, would you introduce yourselves?
Hey, I'm Michelle. Of course, we talk over each other.
You go, Michelle.
I'm Michelle, and I'm in lovely Charleston, South Carolina, where we have some really great weather today, actually.
Hi, I'm Siobhan. I'm in Wellington, New Zealand, and yeah, we've got nice weather today too.
Okay, this is Al Lamperti, outside of Philadelphia with 6 inches of snow. I'm one of the volunteers transcribing on the laptop. Nice to see you, Lindsay.
Excellent. Thank you so much, Al. I can see the snow streaming down behind you. That's what it looks like.
Snow is visible to us, Al.
Great. So thank you again, everyone, for joining us. Let me go ahead and give you a little bit of an update and some framing advice today while we do this Hangout. If you'd like to send us questions, you can use the hashtag DASCH, D-A-S-C-H, DISH, D-I-S-H. You'll find that it's already been shared a little bit on Twitter if you're on Twitter with us. You can also send us direct emails, transcribe@si.edu, or you can make comments on the Google Hangouts page. If we don't get to your question today, we'll make sure that we follow up and link back in with you and try to get some answers to your questions. Also, I wanted to thank all of the people who are joining who may be new to transcribing or haven't transcribed with us yet, but are excited to watch this broadcast. Perhaps some of our friends from Sky and Telescope, and Astronomy Without Borders, as well as other Smithsonian audiences. Let's get some stats on the DASCH project so far. So Lindsay tells me we're completing some of these projects within 1 or 2 days, which is really, to borrow a phrase, an astronomical rate of completion on these projects. We have 4,615 pages completed of logbook pages, and if you've done any of this transcription, you know that that is quite a substantial amount of transcribing. We also have completed 43 projects so far, and 461 people have contributed on the Transcription Center to this project, so it's a really great collaborative exercise as well. We'll go ahead and move into chatting with Josh now. Josh, real quick as we get started, would you give us just a little bit of a background and tell us more about your role? As I understand it, you're one of the longest tenured professors in your department, and you have been around to see these logbooks and glass plate images move through various stages from actual documents and into digitized state as well.
Yes, well, I have been here for quite a while, since having been a graduate student here, my Ph.D. work back in the early 70s. And at that time, the Harvard plate acquisition, or the whole plate project, was still very much ongoing. It had just resumed, in fact, after the so-called Menzel gap, when Donald Menzel closed it down. And it went on, as you may or may not know, up and through 1992. I remember well when I was on the faculty after 1976, I guess just to give you a little bit of history. So I have been here on the faculty for a good long while, had many students. But this project is something that I thought about just very quickly even in the late 70s, believe it or not, because I was using these plates in the original way they were used, with a handheld loop or eyepiece, 1 star at a time. And my interests then, as they are now, are in what we call high-energy astrophysics, X-ray sources, accretion-powered objects. I'm going to tell you about some of this in just a few minutes. And so by the 80s, I thought, I wonder if we could do this. CCD cameras were becoming available. And it took about 5 minutes to realize, no, we can't do this yet because we don't have computer power up to the task, and we couldn't begin to afford all of those expensive disks to store the data. So I put it off for another 10 years, and finally in 2003, it looked as if the time were right or getting right. It still was rather terrifying, the amount of data we would deal with. But that's when I started this project with the first proposal to the National Science Foundation, which was accepted, and we began in 2004. So here it is, 11 years later. We're now in full production mode, and as you'll see, we should be able to finish in about 2 years. The actual scanning is going very well, thanks to Lindsay and David's help before, and other people working here. So you'll see what this is all about.
That's fantastic. Thank you so much, Josh. Well, would you like to go ahead and lead into some of the material you're going to share today, or is there anything else you'd like to tell us first?
No, I think in the interest of time and having time for questions, I can just start.
Great.
So we're gonna do the full screen mode, and I can go into that right now. If everything, I'm going to lose you all from, but you're going to hear me.
We're ready.
Okay, let's do it. So, 1 second here. So I've got a number of slides. This is PowerPoint, and let's make sure we get this all working the way we think it will be. Okay, does everybody see my screen?
No?
No?
Not
Hang
yet.
on. Nothing there, Megan?
No, I see your face at the moment, so let's see if we can...
Let me go back. I know what I did wrong.
Okay.
I thought I was in sharing mode already, but apparently not. Okay, yes, I had gone out of screen share, so excuse me. You will.
No worries. We have plenty of time.
Yep.
We were excited to hear what you're going to share.
Okay, so this should come up.
Yep, so it's loading now.
All right.
Now I see your slides.
Okay, so we'll go into full screen mode again. Just 1 second. And then I will guide you through this. Okay. So I had a little fun with the title here, having just recently seen, which maybe most of you, or at least some of you, have seen, the wonderful Stephen Hawking movie. DASCH is about time, so I'm going to tell you about a new brief history of time. I can't resist the pun, if that's the right descriptor, on Stephen's wonderful first book. But anyway, it's about not only how the Harvard plates and the famed women computers that I'll tell you a little bit about at the beginning of this talk operated and what happened, but how DASCH actually works and how it's enabling now a totally new look at a very major and, might I say, hot field of astronomy that we call time domain astronomy, the study of variability of objects. DASCH, of course, does this on 100-year timescales. So that's what we're going to go hear about. Very quickly, this is just the outline of what I'm going to show you. Brief history of the plates and the computers, the women computers. A little bit about Henrietta Leavitt's very famous discovery. And I won't have time to say much about the modern era use of the plates, but I'll give you a few quick examples. And then we will move from history into DASCH, how DASCH works, how DASCH compares with other projects, why it's relevant. A little bit about the scanner that does all the hard work, and the data releases, and I'll come back to this when we get there, but there will be a new data release from DASCH in 2 weeks, March 15th. We will do that. And then what I hope you will find the most interesting part, some of the science that we're now already doing. There's a lot happening right now, and I have results that I would love to show you, but there isn't time, but we could do this again if you want. You could hear in a few weeks about some new things that we've just been finding that are a little bit too early to show you today. And we want to wind up with questions and discussions. So the Harvard Observatory has this enormous collection of glass plates, 500,000 plates, probably closer to almost 600,000 if we count them all, including plates showing spectra of stars. For DASCH, we're not digitizing those except in a few cases where the spectral images are stellar-like enough that we can use them still for variability information. But by and large, we're not doing the spectra. That can be done later. So a good 500,000 of those. It covers 100 years. I should use my mouse here so we can follow along. 1885, this began. Edward Pickering, who you'll see in a slide or two, the director of the Harvard College Observatory, began this project, and as I mentioned already, ran through 1992. There was a 17-year gap when Donald Menzel was the director, and he said, "Why are we doing this? I'm a solar physicist. I don't think we need to keep taking repeated images of the sky forever." Little did he know that what Pickering already had anticipated in 1885, that by doing this repeated imaging, you have access to a totally new dimension of understanding the cosmos, namely how things vary in time. So you've got to keep doing it. And the other part that Pickering deserves enormous credit for back in 1885 is that he wasn't content just to do this from Cambridge, which was a pretty dark site still in 1885, but he immediately set up telescopes in the southern hemisphere, beginning in Peru, in Arequipa, which was an incredibly bold thing to do in 1885. And Harvard then was a very different place, a sleepy small college, not a big research university, but Pickering managed to do it. Okay, so here's the observatory the way it looked in 1900. Lots of small telescopes, domes all over the place. This one is the Great Refractor. That's still there. This one that I'm pointing to with the mouse, this building is where the DASCH project is adjacent to. Actually, we're now in a building that's just in front of this. That is where all of the scanning takes place, but this building is right next door and is still there. So let me get rid of this picture so you can see the rest of the words here. 500,000 plates. They are typically 10 by 10 degrees of sky. Many of them are 20 degrees on a side, some even 30 degrees. So these are huge, big chunks of sky. The more sensitive plates are typically 5 by 7 degrees, of that order. And if you've got 500,000 plates, and let's pretend that they're 10 by 10 degrees, all of them, that's a typical size, you wind up with 1,000 to 2,000 images for any place on the sky. And if you take those images and make them random in time, filling that whole 100 years, that means you get an image typically every week or every month. Sometimes you get them every day. But so they're not in any strict order, like once a week on this spot of sky. And that actually is good. I don't think Pickering had this in mind, but it was wonderful that he set it up this way, because it means we don't introduce strange sampling of the data by having it on some kind of clock-like basis. And again, the key thing, this full sky coverage is really critical. That makes the Harvard collection really unique. Here is one of the telescopes used, and this is the 24-inch Bruce. David, am I right in that? I think I may have misattribution here on this image. Let's not worry about it. But there are many such telescopes that were used. Actually, the total, if you go to the DASCH website, and I'll show you a link to that in just a second, and I hope at least some of you, or people hearing and not actually calling in on this, have done that. You can learn all about the telescopes used and how many there were. There were about 40 telescopes, of which 10, in round numbers, were the principal ones. From very small aperture, only 1.5 inches, to 24-inch. The Bruce telescope was of that aperture. So why did Harvard do this? Why did Pickering do it? It was to understand what makes the variability in stars. Not the periodic variability that a binary system, 2 stars orbiting each other, those were well understood in 1885, but the irregular variability was not understood. And it's still not understood in many cases, but we certainly understand a great deal more, and that's where the exciting new physics comes as well. So here are some historic images of the observatory, that building I pointed to, which is right adjacent to where we're operating now. These wooden cabinets storing the plates that were coming in on a roughly weekly schedule, maybe every several weeks. Plates being shipped back from Peru. At least one plate shipment was lost when an entire ship went down due to a German submarine attack. So this was, you know, high seas, high stakes operations that were going on. This whole operation or project began before the Panama Canal, so to get from Boston to Peru meant going around the tip of South America, so this was big stuff to be doing. Shapley built a new building here, which is where we still have the project operating today, to house these plates. And of course, Pickering, as I'm going to tell you in the next couple slides very quickly, had this wonderful group of women computers in quotes. They were doing computational work. This was, of course, many, many decades before a computer in the modern sense of the word, but they were doing calculations. They were reducing the data. They were analyzing the images, if you can see where I'm pointing the mouse here, to produce light curves. That's a record of how bright a star is on the y-axis versus time on the x-axis. And so that's where the discoveries came from, studying variability with this amazing group of women that were doing this. Well, Henrietta Leavitt is the most famous of these, deservedly so. And every Astronomy 1 textbook describes Henrietta Leavitt very appropriately. What she did was observe luminous, very bright stars in two nearby galaxies, very nearby galaxies that we don't have the good fortune to see from the northern hemisphere, but from Peru you have a beautiful view, or Australia, or any place well south of the equator, the large and small Magellanic Clouds. So what she did was, on these stars that she had already determined to be variable, by making repeated observations over and over again, she could make a plot such as this schematic one. This isn't Henrietta's original artwork here. This is just a schematic representation of the brightness of a given star versus time, that it was getting brighter and then dimmer and then brighter and then dimmer on a time scale of days, as you can see in this schematic illustration, 6 days to go from peak to peak. Okay, that sounds interesting. Why is that so exciting to be, you know, required reading, and deservedly so, in every astronomy textbook? The reason is, and this is where she deserves enormous credit, by looking at a galaxy, a huge group of stars, similar to our own galaxy in this case, but about a tenth the total size and mass of our galaxy. But by doing so, looking at the large Magellanic Cloud, and I'll show you a picture of that in just a minute, she knew, anybody would have assumed, and this is a very reasonable assumption, that these stars are all at the same distance. So what she observed was that stars that had a longer period, time between peaks, were brighter on their average brightness than stars that went bing, bing, bing much faster. And that relation between the period of the variation and the luminosity, that's the intrinsic brightness of a star, we now give the name to as the Leavitt law. It's still referred to in older textbooks as the period luminosity relation. This is what her discovery was, and now you're probably still saying, so what? Why is this so dramatic? Well, what this enabled is, if you know how intrinsically bright a star is, and you know how apparently bright it appears to you, what you measure in these funny units we use in astronomy called magnitudes, you can deduce the distance to the star, or to the galaxy in this case, the large Magellanic Cloud. And that was tremendously important, and it enabled Hubble. Surely everybody's heard of Hubble, and we now have the Hubble Space Telescope. It enabled Hubble in 1929, only 15 years after Leavitt's discovery, which was in 1908, to determine that the universe was expanding, because he could measure the distance to galaxies using this relationship. So very important stuff. Let me show you Henrietta here in one of the iconic images. I think this is from roughly 1915. I couldn't find an actual date. I'm sure it could be found, but it doesn't matter. Here she is working here at the observatory. can almost claim to recognize the walls in the background, but I won't go that far. Here's another one of these very important women, and I don't have time to go through all of them, but Annie Jump Cannon. This photo must be somewhere around 1920, roughly the same era. She's the one who devised the whole relationship between stars' color and their spectrum. The spectra were taken on the plates that show spectra that I mentioned that we're not digitizing for variability, but that produced the Harvard spectral sequence that is the foundation of our understanding of how stars live out their lives, like our sun, and it was the beginnings of the whole understanding of how stars evolve. So what she did from the Harvard plates, here she is examining one with an eyepiece, was absolutely fundamental. And the third example, not one of the computers per se, a little bit later in time, but here she is, Cecilia Paine. She later married Sergei Gaposchkin, Cecilia Paine Gaposchkin. I knew her. She was still around here in the 70s. She was a remarkable woman. But an incredible discovery that she made. She was the one who deduced what the sun was, that the sun was made of hydrogen and helium and not iron and Earth-like elements. It had iron indeed in its spectrum, but the leading theorists of the day assumed from the spectrum, because they were not taking into account proper, then very new understanding of atomic physics, that the sun was very much like the Earth in its composition, the elements in the sun. All the elements in the Earth are indeed in the sun, but in a very, very different proportion, where 90% of the sun is in hydrogen, 10% helium. That's by numbers of atoms. It's 75, 25% roughly by mass. Very important discovery, again, made here in the same era. This is 1925, her thesis work. So I'm going to quickly go on now. There were many other discoveries in these early days of the plates. Shapley, the director, Harlow Shapley, doing studies of galaxy distributions, which led to understanding of galaxy clusters. The very first indication that there were galaxies that we now call active galaxies. I'm going to come to those at the very end here. And jumping ahead a few more decades, when quasars were discovered by Martin Schmidt at Caltech in 1962, within 2 months, Dorrit Hoffweit, another remarkable woman, she was one of the women working on the plates here as well, not in the very earliest days, but in the 20s and 30s. And Harlan Smith immediately discovered from the same Harvard plates that we're now digitizing that this object, this first discovered quasar, was variable, and that was an incredible discovery because the variability of something that luminous, distance being determined by the Hubble law, meant that it had to be very compact, and we now understand it to be a supermassive black hole. I'm going to show you a DASCH light curve of this object at the very end. And finally, X-ray binaries that I am interested in, as I'm interested in these things. The very first, most luminous one of these in the sky discovered, this is a typo here, sorry, Elaine Gottlieb in 1976, and Bill Liller, who is a professor here in the department, a colleague of mine, discovered the first binary period. So a lot happened in those early days. So let's quickly now look at the plates and the scanner and how DASCH works. I invite all of you transcribers, if you are ever in Cambridge or Boston, come over and you can see this for yourself. But in the meantime, this is what 500,000 plates looks like, a very tiny view of down one of our very crowded hallways. Thousands and thousands of plates. They're all 8 by 10 inches, the size of your computer paper piece that you would have in your printer. 30,000 of them in round numbers are bigger, 14 by 17 inches. So they fill 3 floors, there's 200 tons of glass, and they're beautiful to look at. Here's the Large Magellanic Cloud. You can go to the DASCH website and see these images. I've just put them up here for viewing right now. This is where Henrietta Leavitt did her remarkable work discovering these Cepheid variables. This could be, if you can see where I'm pointing the mouse, that could easily be a Cepheid in the LMC. That's roughly what one of these would look like. Halley's Comet over here, 1910 passage. Some of you may have seen the 1986 passage, which was a terribly disappointing thing from the northern hemisphere. This is what it looked like from Peru in the previous passage. Beautiful images. And finally, those of you with binoculars and looking up from your backyard sky surely like to look at Orion. It's one of the most gorgeous things one can look at. This is the 3 stars in the belt of Orion here, and right here, this fuzzy patch that probably doesn't show up too well on your screens is the Horse Head Nebula, discovered in this beautiful plate taken by one of the B series plates taken from Peru in I believe, 1899. I'm not remembering the date, but it's roughly that date. Okay, so the plates all this time, up until we started this project, have all been analyzed, looked at, all this science, a huge amount, done in much the way that you see Alison Doan, our curator of the collection, doing here. A plate's on a light table, you're looking at it with a handheld eyepiece, and you do 1 star at a time. So these 500,000 plates might have had, typically, these are just round number guesses, a few stars, maybe tens of stars in some cases, out of the 50,000 stars on a given plate that have been studied. DASCH is now making possible to study all the stars on all the plates, all of them that are resolved that way, because we can do blind searches for variable objects, as I'll show you. So why are we doing this now? Well, as I've already mentioned, this whole time domain astronomy business is a very hot field. There are projects going on big scales to do this, and DASCH is serving this in a very unique way. But why now? Once again, it's because we can do it now with computers and with data storage to store the enormous amount of data, roughly a petabyte of data. That's 1,000 terabytes of data that the project is producing or will produce. So DASCH complements LSST, which is the highest priority U.S. project in ground-based astronomy, funded by the National Science Foundation, primarily, that is now being built. Here's a web page you could look at if you're interested in learning more about LSST, but I won't have time to tell you. But it's very complementary because this is time domain astronomy going much deeper than DASCH, but what DASCH enables are discoveries of very rare and very luminous things that might have been discovered by LSST and vice versa. So the reason for this project now then is we can study the very long recurrence times of things that are very, very slow to repeat, things that are enormously luminous and happen therefore very rarely, and we have lots of examples of this kind of phenomena, which are some of the most extreme things we study in astronomy and physics. And once again, just from another standpoint, things that are very rare, whether they're luminous or not. So this baseline of 100 years is absolutely critical. I'm going to skip this slide, just show you for a few seconds, and then won't have time to describe it, but this is showing you if we make a big landscape view of how luminous something is on the y-axis versus how often does it repeat from centuries down to days. DASCH covers this whole blue hatched region here, whereas LSST and the modern surveys, because they obviously don't go for 100 years, are this left-hand portion. So the classes of objects that you see in the boxes here show you all the things you can study when you have access to this. Very quickly, how does DASCH work? The scanner, you can go to the website. Here's the link, dash.rc.fas.harvard.edu, and look at a little video clip. We're going to put a better video on there shortly. It's a bit out of date, the video, but here's what we do. We load 2 plates on these platens here. The plates are loaded in. They are imaged when they're loaded in by this very fast CCD up top. The telecentric lens gives 1-to-1 imaging of the plate onto the CCD, so we're looking at only 40 by 40 millimeters of the plate. And we illuminate the plate from below with an array of LEDs, light-emitting diodes. All of this whole process, everything I've described here, taking only about a second. And then the table moves by half of a image diameter, 20 millimeters, that's about 3/4 of an inch, and we do the whole thing again. An entire 8 by 10 plate here like this takes 45 seconds to convert into a digital image, to get all of these 60 exposures that are then stitched together by the computer. We then operate a very massive pipeline computer pipelines, several 100,000 lines at least of code to do complicated processing to take these photographic images and turn them into digital images, which are what you can yourselves go and download online and use to do your own analysis of objects. And you can do this because part of the reason for making these data available, in fact, the major reason, was to give access to the whole astronomical community and the public. You, the transcribers, your nephew who's keen on astronomy, you can go to the DASCH website and you can look at images and create your own light curves with these data releases. This is a map of the whole sky in a coordinate system that we use in astronomy called galactic coordinates. This is the galactic equator, plane of the Milky Way, center of the galaxies here. We started from the North Galactic Pole, and we're now down. We're going to release, as I mentioned already, in just 2 weeks, the 4th data release, DR4. And we're going to just keep marching our way through the sky. This will be part of the announcement that I'll make, because it's a change from what we had previously announced. We're just going to keep going all the way down until we reach the South Pole. Originally, we had planned to do the order of scanning in a slightly different way. And at the rate that we are going now, we are doing this quite a bit, like 3 or 4 days a week. We're doing 400 plates a day, or close to that, but we will be doing 5 days a week, 400 plates a day, starting in April. And at that rate, we should finish most, if not all, of the imaging plates by the end of 2017. So how do we deal with the images? How do we convert them into light curves? Very quickly, I've got to speed this up. We calibrate them on catalogs that we now have, beginning with the Hubble Guide Star catalog, that tell us the average brightness of every star over the range of brightness that DASCH is sensitive to. We calibrate instrumental measures of brightness from our direct digital images versus what we know their average brightness to be. Most stars are not variable, so this allows us to calibrate the whole plate. We do it in concentric annuli, as you can see here, because the sensitivity of the plate or the telescope originally falls off from the center towards the edge. And we produce light curves. This is what you can do directly on the website. It's all explained to you how to do this. Magnitude versus time here. And here's just some random star, which is absolutely constant, as most stars are. This is how we can calibrate. But we could do the same thing on an object. In this case, I've just picked one that we knew or know already as a variable. This is a well-known eclipsing binary in a cluster, the Beehive cluster, M44. And you can see these enormous variations in magnitude. Sorry, the scale got dropped off the left side, but this is about a 3 or 4 magnitude dip. And because we could discover, if we didn't already know, this is an eclipsing system. It's periodic, but we can directly on the light curve fold the data to see what the data look like folded on the known binary period here, which is 1.09 days for this particular system. And the reason I'm showing you this is not only to show you what you can immediately do with these data, but to try to bring this home to you, the transcribers. This point, which is repeated here, this plot, as I've put in this little label here, is repeated twice for clarity. This is the way we, in astronomy, present these light curves. Here's a point that tells us, my God, we've got the wrong time for this point, because it should be over here. All right? The magnitude is correct, but it's the wrong time. This is the time between 0 and 1 of the period, which is 1 day. So this is 1 day worth of time, but we've taken 100 years of data and divided them up into what fraction of that period was each and every data point taken. And it works for all of them. We can see this eclipse dip here, which is also a little broader than it probably should be, which may reflect timing errors. But this one is way off. Check the logbook. So we will do that. Haven't done this yet, but I just noticed this today, just putting this slide together. Very quickly, some of the discoveries. These are on the website, so I'll go through this very quickly. We've discovered in the early days, my first graduate student on the project, that normal stars, red giants in this case, of a particular color and temperature, are doing long-term variations that we had never seen before. This is not the kind of variability that we had discovered before. We have 2 possibilities for how this could be arising, but neither one of them explains all the facts. We've discovered in the same early days, a couple of years ago now, types of dips that are much faster in duration, shorter in duration, in this case due to a binary system where dust is being transferred and evaporated as matter is transferred from one star to the other. We've discovered, this was one of the exciting early discoveries, a totally new type of nova. We call these symbiotic novae. They're a particular class of novae. Novae are stars, white dwarfs that are getting matter dumped on them from a binary companion. They normally last a few months. This one lasted for 5 years and produced no nova remnant, nothing blown off the white dwarf. That's a very important discovery because it means that this is a candidate kind of system for the type of system that can produce the most luminous supernovae, the so-called supernova 1As, from this kind of a process, because the white dwarf can continually gain mass. And finally, just because I know I'm running over already, black holes, which are my own particular interest and many others. We've been looking, this is one of the motivations for DASCH, looking at black hole low-mass X-ray binaries, which we knew before we started DASCH, are transient sources. They're typically off. They're not bright in X-rays or in the optical. And every 50 years or so, they produce a nova-like outburst, but nothing to do with the kind of nova we saw on the last slide. Here's an example of one where this is an object that was discovered for the first time. It has this funny-looking catalog name. It was discovered by the Gamma Ray Observatory, GRO, in 1994. And because of an outburst, which then allowed it to be identified as a black hole with a binary star companion, here it is back in the 1940s, undergoing an optical outburst, dim, bright, bright, and then a few months later, it's gone. There are more points in between. This was the first of these that we discovered. There are 3 others. I'm only going to show you one more example. This one is a particularly dramatic one. In 1901, a huge outburst from this system, which is a variable star name, but only in 1999 discovered to be an X-ray nova and a black hole system. And almost identical in its outburst duration, very fast outburst, to what was discovered in 1999-2000. So we've got 4 of these things, and there are more now that will be coming because as we're going into the galactic plane, we're going to see many of these things. But why is this exciting? Well, if we take the amount of time we were able to look at these systems, that's what this plot is showing you. All the yellow here is indicating where we could have seen an outburst. So for this one, we see almost complete coverage. We couldn't have missed any. This one is less well sampled. This one is the poorest sample. That's that one I began showing you. We can do analysis on those amount of time we could have seen an object versus how many we did see. And that tells us something that we call the duty cycle. What fraction of the time are these things on? And so that's what these numbers are, telling you that these objects are only visible for 1% at most of the time. In fact, our more recent results are showing that it's even less than that. Why is that exciting? Well, if we compare that to very similar X-ray binaries that don't have black holes in them, but have neutron stars, very close to being a black hole, but not the same thing. They are on for 10 times longer, 10, 11% of the time. Why is that interesting? Well, it's because if we take the total number, total number of objects that we should have to produce neutron stars versus black holes, which comes from something that we call in astronomy the initial mass function. That's the number of stars there are of any given mass. We find from just these early results from DASCH that we are getting 25 times more black holes than we should have from the ratio of neutron stars to black holes that nature produces. That doesn't mean that our understanding of stars producing neutron stars or black holes is wrong. There may be some corrections needed. But what it's almost certainly telling us is that we've not had the right picture all this time for how we produce these exotic binary systems. They're probably produced by dynamical encounters which favor black holes. So that's very exciting. I'm going to finish here with variability of quasars. This is this quasar 3C273 that I mentioned before. Here's the DASCH light curve. You can see something like this yourself by just typing 3C273 in the search box on the the search light curves page. And if we blow it up, which we can do with higher resolution plots, we can see that there's all sorts of variations going on. What's really interesting, though, is when we compare 3C273, here's one of the Harvard plates, now showing you an image of the stars. There's our quasar. These are all reference stars that we can just do the identical kind of analysis on. And here's a light curve of one of the reference stars. Doesn't look anything like 3C273, obviously. It's dead constant all the way across, as it should be. Well, here's the bombshell. When we look at the variability of this quasar on a 100-year time scale versus all 10 of the reference stars in this particular kind of analysis that is telling us how much power does the object emit versus frequency, versus time scale. So I should have given you a version of this plot that has years across the top, and I'm sorry I didn't, but here's 16 years. The two lines here indicate where anything above these lines are highly significant. So bottom line, all of the normal stars are down here. They're well below. This is a logarithmic scale. 3C273 is variable, as was known in 1962 by that first analysis of the Harvard plates. But none of this was known then, because we didn't have 100 years of data all in digital form to do this kind of analysis. What we've discovered here is that this object, this quasar, which is a supermassive black hole, 1 billion times the mass of our sun, is doing something remarkable on 16-year timescales. We don't understand this. This had been suspected from some earlier analysis of the Harvard plates, but this makes it totally convincing. It's maybe precession of the jet, but we don't really know. And I'll finish up here, the very last slide, to show you that if you think that's remarkable variability, here is an object that we've known is a very bizarre quasar-like object, but nobody has seen a flare that is 4.5 magnitudes increase in brightness from this object, as this point is here, and lots of them up at 2 to 3 magnitudes. Peak to peak, this is more like 6 magnitudes. So enormous variability. Back to the point I made before, a very rare event. Here's 100 years of data. It isn't continuously covered. There's more data to come. That's where your logbook transcriptions come in, but already discoveries that we couldn't have anticipated. So I'm sorry for running over, but let me just quickly wrap up. The project is working very well. It is complementary to modern time domain astronomy projects in a big way. The public can get at the data. The astronomical community already is. Full speed ahead. This thing will be done in the next couple of years. This plate cleaning machine has held us up. It's now just about ready to work. It is working, in fact. And the logbook metadata, thanks to all of you wonderful transcribers and who are listening, what you are doing is enabling the remaining 20% of the plates to get into this database. And the best part is that the plates that are still missing, that 20%, are by and large the best plates. So we're very keen, very anxious to get this done, and we're very grateful for your help. So let me stop, and I'll get out of this screen mode here and ask for questions if we have time for that, Megan.
Yes, thanks, Josh. Quickly, for those people who are watching who have thoroughly enjoyed the talk as we have, but have never seen the Transcription Center, I'd like to just really quickly show you where to find the logbooks in the Transcription Center so you can help get at this best 20% that's left, all this extremely rich data that's going to help us help the DASCH project move forward into new discoveries. So let's see, we've got, if you come to the Transcription Center homepage, you can use some of these windows where it says projects above. I'm showing you the project page for the Harvard-Smithsonian Center for Astrophysics, and you'll see right now, for example, there are several logbooks that are posted, and the reason is because we're going through so many of them, 1 to 2 days per logbook. And you'll see that you can join in this transcription effort by transcribing or reviewing. And for example, the first logbook here is 50% complete. It means it's been 50% transcribed and reviewed. And a little bit of yellow means that someone has transcribed it. It's not been reviewed yet. And the gray part of the bar means that many pages are left. So out of 109 pages, there's probably about 50 left that can be transcribed, and maybe a little bit more than that that can be reviewed as well. So join us in the Transcription Center, which is transcription.si.edu, and help the DASCH project develop some of this data so we can move forward on what appears to be ever-increasing discovery and an amazing link between historical data and contemporary research data as well. Let's turn over, I'm going to stop screen sharing now. Let's turn back over to our volunteers who are in the call if you guys have any questions, and then I'll follow up at the end of your questions with some that have come off of Twitter. Anyone want to jump in?
I've got a question that sprang to mind basically when I heard about the German submarine sinking plates. Has any scientist, when they're doing work on the plate prior to preservation of them and digitization, has anyone actually dropped a plate and smashed it?
Oh yes. Yeah, that's inevitable, and there have been some, embarrassing accidents. We don't mind, revealing those, but dropping them is, well, Lindsay could probably speak to that better than I. She's down in the stacks right now.
It happens now and then. We're really good. We're really gentle usually, but every once in a while something happens. It's just, human error. It's going to happen, but we're pretty good.
No, it's incredible what Lindsay and our crew are doing, because they're moving a lot of glass around on and off of a very sophisticated machine, the scanner, and soon on and off of another sophisticated machine, a plate washing machine, because all of the backside of every plate has to be cleaned, fingerprints over 100 years, all that good stuff. So there's a lot of stuff happening, but it's amazing how few plates do get dropped. Very few.
What happens when you do drop them? Do you get out the super glue, or what happens?
Lindsay, you want to mention?
Sure. It just so happens that I have one right here for you.
Oh,
what I'm trying to do is mend them. We have a whole cabinet full of plates that have been broken. So I'll just show you one here. This one, obviously, I don't know if you can see it. It wasn't broken very, very bad. So if it's just in 2 or 3 pieces, we can usually attach it to a piece of glass and then stick some archival tape around it and put it in a new jacket. So that's usually what happens.
And the computer can stitch those 2 halves together again. It's amazing what you can do. If it's a lot of little pieces, then no, it's gone. But maybe up to 3 pieces. Okay. Other questions?
I actually just wanted to say a quick thanks for doing this for us, because we really love to hear about how what we're doing is helping science, because I know that's why a lot of us are here.
That's great. Well, as I've said several times, we are really grateful. You really are helping. And the plates, the logbooks that are being done, it's as I wrapped up and mentioned, they really are the very best stuff, which we've been waiting on. So a lot of those light curves will have more of the most crucial points. One of the things I was going to show you today, and I thought it's just a little bit too soon, David hasn't heard about this, we've discovered an historical example, as all of DASCH is, of course, of a black hole eating a star, a tidal disruption event, David. And
cool.
we're probably going to find many of these, but they're typically all down around 15th or 16th magnitude, where we need those B plates and the MC plates, and so they'll come. But that's where this is really going to be exciting.
Thanks so much for answering those questions, Josh. I have a few that have come in off of Twitter. One is a little bit related to what you just said, and this is actually from one of our volunteers, Mario, who's unable to join us today, but is a frequently contributing member of the DASCH project team and the Transcription Center. And he'd like to know if there's anything new scheduled after the transcription of these logbooks.
New for volunteers, or what?
I think the question might be about the extension of, is there a new pathway of research that you're interested in pursuing after these sets of logbooks have been transcribed?
Okay. Well, there's an enormous amount of science to do with these plates, and so they're all related, or most of them are related to things that I mentioned. But
hey, Josh, can you exit your screen sharing?
Yeah, I'm trying to do that. One sec here. That's. I had to get back to the right window. Sorry about that. Okay.
Perfect.
Okay. So If the question is from Mario, if it's about things that are DASCH related, I'm still not quite sure what he was asking, whether it's DASCH related or just other things in general.
I believe from the Center for Astrophysics, but also extended out of the DASCH project. Okay.
Well, from the Center for Astrophysics, I mean, from the other things that I do, I can only speak for, I guess the question is, what are my interests? Yes, there are other things that relate to DASCH. Let me try to make it very, very quick and succinct. Black holes, as I've been saying, are incredibly interesting and objects that have lots of different ways of being able to approach them. The other way is to detect them not from their historic long-term activity, which is what DASCH does so uniquely, but to do it now and in the future with new X-ray telescopes, which is where that's the way we discovered black holes in the first place. So I've had a project here for some number of years to develop X-ray telescopes that are similar, and this is actually kind of an interesting comparison, similar to the Harvard plates, something that can give us a very wide field view of the sky for this same reason. When you don't know where something's going to go bang or go off, the only way you have any hope of finding that and then studying it and trying to understand these amazing things that nature has cooked up for us is to look at as much of the sky at the same time as you can. So we're working on telescope designs that will enable that. That has to be done in space, so these are NASA projects, and that's something that we do hope to be doing in the next few years.
Great, thank you so much for sharing that, Josh. And then actually two final questions from Rick Ferrante, who works with Smithsonian Institution Archives and brings in a lot of scientists' field notes into the Transcription Center. He was wondering, with those optical outbursts, is there any effect on things like gravity? And the second question is, are there types of data that have been captured on the plates that you didn't notice or were unable to really see clearly until they were digitized?
Okay, first question, when these outbursts, the black hole X-ray binaries, or the outbursts from these quasars that I wound up showing you, those have no effect on gravity. The mass of the black hole is there. In the case of the quasars, these are, incomprehensibly large masses, 1 billion times the mass of our sun, an object that's the size of our solar system. That's the definition of a quasar. And so the mass doesn't change, but the energy involved in one of these outbursts is absolutely, colossal. Have we discovered things that could only have been seen on the DASCH with the digitized plates? Yes, we have. All the examples I showed you would have been very hard to pick out. In fact, I'll venture to say impossible. Those first stars I showed you, red giants with these long-term 100-year variations, that would be very difficult to do the old-fashioned way when you had, first of all, no idea which stars to look at. Because from plate to plate on a given month-to-month basis, you would see very little, because it's varying over time scales of decades. So that's definitely the case, that DASCH having this ability to do everything at once opens up a whole new domain.
Excellent. Well, thank you so much. Al, did you have any questions that you wanted to ask? I know you get the opportunity to interact with some of the DASCH team in person.
Yeah, I highly recommend any volunteers, as was mentioned, who are in the Cambridge area to take a tour. It's really neat to be very close to all this history and actually see it up close and personal.
Excellent.
So, yes, we welcome you all, those online here or on the call, and those who are, watching remotely or whatever.
I'll try and get there. It's a wee way away, but yeah, if I'm ever in Boston, you bet.
Oh yeah, please do.
Same there. Okay, well, thank you so much, everyone, for joining us. Thank you, volunteers who are watching, and folks who are watching who are not yet volunteers in the Transcription Center but would like to come and transcribe logbooks. Again, you can find these logbooks at transcription.si.edu. But I'd like to thank you for being here today. Thank you so much, Josh, Lindsay, and David, for helping to bring this project together, this moment together. And then we also hope to have some follow-up hangout time, perhaps after we've released these new discoveries. Sorry, you have released these new discoveries. I'm just riding on your coattails here. And also, we would like to remind volunteers, if you'd like to communicate with us in social media, you can find the Transcription Center at transcribe.si. We're also on Facebook and on Tumblr, and you can communicate with the DASCH team using @DASCH as their Twitter handle as well. And David also has a Twitter handle @DavidSlisky. So thank you again, everyone, for being here. David, one last thing you'd like to say?
Yeah, so for more exciting news and just kind of a popular article, Sky and Telescope will feature both an article about the Transcription Center and a full spread on the DASCH project itself coming up in May. So if you look forward to that in about 2 months, it'll be on your newsstands around the world.
Yep.
Wonderful. Thank you so much.
If I can quickly interject here, I want to thank you, Megan, for putting this together and hosting this. Wonderfully done. Thank you.
Thanks very much.
Yes, thank you.
Well, hopefully, everyone, we will have the opportunity to get stuck into this last 20% of amazing data in the logbooks and push forward on sharing it back. And we will continue to update all of our volunteers and the DASCH team on the progress of these logbooks and see where we head up next with material that may come in from Center for Astrophysics. Again, if you have any questions or you'd like to get in touch or have feedback, you can email us, transcribe@si.edu, and also feel free to share this link out with other people and ask, hey, best recruitment is through friends and family. Thank you so much for being here today, and we're going to end this broadcast now and hopefully hear from you again soon. Thank you so much.